Hello, welcome to section 5.9, Scaling the Inputs. Yesterday, we multiplied numbers in front of the function. So like we did 5.2 times f of x. And that was how we created g of x. This was yesterday. We did this yesterday. We multiplied in front of the function. So the question is, what happens when you multiply inside the function? So if you did f of 2x, versus just plain old f of x, or f of 1/2 x versus f of x. That's the question. What happens when we multiply the x first and then see what happens to the function? All right, so here's the warm-up. This is on page 583. Every weekend, Elena takes a walk along a straight road in front of her house, 2 miles, and then turns around and comes back. She walks at a constant speed. So here's her graph. She goes out and she comes back. All right, so we're going to sketch a graph of the function that gives her distance, g of t in miles, from home as a function of the time t if she walks 4 miles per hour. So right now, she's walking 2 miles per hour, right? So this is the graph for 2 miles per hour. She goes out, that's 2 hours, she comes back, right? And so there we are. Now we're going to do 4 miles an hour, so that's twice as fast. So we're going to go out to 2, right? So in the half amount of time, and then she comes back. So she does, in 1 hour, she does 4 miles. So she goes out 2 and back 2. So that's the story with this. Now, what we can do is we can write this in terms of g in terms of f. So we get g of x is equal to f with an x here. So she's going twice as fast. So when we go twice as fast, we're going to put a 2 in front here. So it's 2x. And I made a little baby whoopsie here. It's f of t, so they go at t in time. So what I really should say is g of x is equal to f of 2t, because it's time is the function here, is the independent variable. All right. So what we've noticed on this first page is if we multiply a number times the x first, then do the function, it took the graph and it squished it in. It made it go twice as fast. The heights are still the same. The y values are still the same. It's just the x values got smashed together by this factor of 2. So you got to remember, if it's smashed in, it's going to be something that's bigger than 1. Well, guess what the next example is? It's going to be more spread out because we're going to go slower. We'll turn the page here. You remember the Ferris wheel problem? The Ferris wheel problem was back a few sections ago. Let me pull that up. All right, here's the Ferris wheel problem. So 80 seconds ago, you were at the bottom, and then 80 seconds later, you're at the top. So that's where t equals 0, and then you go up and down and around the Ferris wheel. Okay, so here we go. Here's the Ferris wheel problem revisited. Okay, so we got the g function here. What's happening? The first wheel is twice as high. So if it's twice as high, you're going to be twice as high. So this answer right here would be 424, followed by 362, followed by 212, followed by double that, 62, followed by 0. So that's just making it be twice as tall. Now we want to make a second Ferris wheel, h of t, and the second Ferris wheel is the same height, but it rotates half the speed. Okay, so it's half the speed. So at 0, it's still going to be at 212, right? Because that's your starting amount. So that's the same. At 40 seconds, that's where it's going to be where it was at 20 seconds. Right? So 0 to 20 is going to be 181. 0 to 40 is also going to be 181 because it's twice as slow. It's twice as slow. We can't fill this one in because we don't know the answer for that in-between point. We don't know a number in between here and here. Then we also don't know this number here. Okay, so then at 80, it's going to be what it was at 20 or 40. Sorry, so it'd be 106. All right, so it's twice as slow. So 80 seconds is the same thing as what it was at 40 seconds, and we don't know those two. Okay, so complete the table for G. I already talked about that, why we don't know those, because we don't know those in-between points. Complete as much of the table as you can for the H function. We did that. Now we're going to express G and H in terms of F. All right, so G is the twice as tall. So G of X, twice as tall is what we did before. That's where we multiply by the outside of the function before we do the function. So we'll take twice as tall would be 2 times F of X. Well, I did F of X. They want F of T. So let me do it again. So G of T is equal to 2 times F of T, because it's Ferris wheel. So they want it that way because it's F and T's and all that stuff. Okay, now we want it to be twice as slow. Okay, so twice as fast, we multiplied by 2 here, right? 2t or 2x. So we want it to be twice as slow. So we're going to write h of t is equal to twice as slow. F of, don't put a 2 in there, put 1/2 t. All right? So this would be twice as high. Oops, twice as high, H-I-G-H, twice as high. I was trying to write height and high at the same time. And this one would be twice as slow. Okay? All right, we took care of that page. Now we're going on to this page here. All right, so this one here we have the original equation is, no, it says the function k is transformation of the function p. Oh, p is the original one. Okay, so p is here, and then k is the dashed line. So this is not making it be squished together, it's stretching it this way. So this is what we did the day before. So write an equation for k in terms of p. So k is equal to, so 2 becomes 6. So 2 turns into 6. So 2 times some number is equal to 6. So you got to do that with a multiplying scale factor. Well, 2 times, that's right, 2 times 3. So 3 goes in here. So we're going to put 3 in front of the p function. So it's k is equal to 3 times p of x. All right, so it's 3 times, makes it 3 times as higher. Now on the same axis, graph the function, which is 0.75. So 0.75 is going to spread it out. So it's going to be stretched out. Okay, it's going to be stretched out. So we're going to make it be multiplied out that way. So in order to stretch this out, what we're going to do is we're going to take the points and we're going to divide them. We're going to divide by 0.75, and that'll stretch them out the right amount. So this is 4, right? This is it's over 4. So I'm going to take 4 divided by 0.75, and that's 5.3 repeating. Okay, so down here, there's no axes here, so I'm going to put it right up here in this space. So it's 4, now it's going to be over 5.3, like that. It's still going to go up 2, right? But this is over 1. So now I'm going to take 1 divided by 0.75, and that's going to be 1.3 repeating. So 1.3 repeating is about there, so it's going to be stretched out. So this line here got stretched out to there. It's not going to be stretched out at 0, it'll still go through 0, 0. Okay, this is -1, so it's going to be -1.3 repeating, so it's going to be like that. And this is at 3, -3, so it'll be -3 divided by 0.75 is -4. So it'll be at -4 now, so it'll be over here. And that's it. So when we do this, we divide to figure out how it got stretched out. You divide by this number. And that would apply back to the original page, wouldn't it? So this is 2, and then that number there is what we divided by. So 2 divided by 2 is equal to 1, so notice I put it at 1. And then 1 would be that point right there. 1 divided by 2 would be at 1/2. So see, this went over to 1/2. And then 0 divided by 2 makes it be right there. So that's kind of the key to this. You got to think divide to figure out how it's stretched. When you divide by a decimal, it's going to make it go out farther, right? When you divide by something bigger than 1, it's going to make it be smashed together. So that's kind of the key to this. So this is the number here, right? So we divide by that number. So if the point goes through 1, 2, right? You divide by 5, it's going to go through 1/5, comma 2. That's the story of that. So we divide by that number in front there, and it's going to, this one 5 times as much, it's going to smash it in versus like stretching it out. All right, we'll skip that one. So here's the problem right here. Oops. So in this problem here, we can see that the train's going twice as fast. So 4 became 2, right? So twice as fast, 4 divided by 2 is 2. So this 4 point goes to the 2 point. The 3 goes to the 1.5. The 1 goes to the 1/2. So everything got smashed together because it's twice as fast. So instead of taking 4 hours to go 150 miles or whatever it is, it only takes 2 hours to go 150 miles. So everything got smashed together. If we went the other way, twice as slow, you would take this original thing and multiply it by 2 to stretch it over this way. So twice as slow would stretch it out, twice as fast smashes it together. So you smash it or you stretch it. So that's kind of the deal with that. And then they talk about another train, right? So that would be even slower. So shifting it over even more, right? Because it's even slower. Okay, now the purple page. All right. So we're changing G. No, we're changing F to make G. So this is going to that. So we're going from here to here. This is F. We're changing it to G. So it's hang on a second. I think I just said this backwards. My brain's rotten. So from here to here, it's 3 times as slow. So it got stretched out. So when it gets stretched out like this, you got to use a fraction. So by 3 times as much, that means that it needs to be 1/3 x. right? So we took the original value, 10, and we divide it by 30, and that equals 1/3. So it's the original value to the new value, original value to the new value. That's how we figured these out. Original value to the new value. So original and then new. That's another way to do that. Okay, so if we go to this one here, this is tricky because we're going, they keep switching these on me, so it's messing me up even. So the original was dashed, and then it's changing to G, which is solid. Now you look here, G is dashed, right, and F is solid. They did it backwards for us. So we're changing this number into this number. So what do? We take the original, goes on the top, right, and you divide it by the new. Original divided by new, and that's your factor, and it's going to be a fraction-y thing because it got smashed out. So it's original divided by new, and you're going to put that in front of the x. So you're going to G of x is equal to F, and then blah 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 x, and you're going to put the number in there. This one here, it's going from F, which is dashed, to G. Okay. So this is getting smashed in, so this is going to be a greater than 1. So you're going to take the original divided by the new. Original divided by new. And that's your multiplying factor. Here, two things happened. It got flipped over the x-axis. So that's going to be a negative. So it's going to be a negative, but then here's your original changed to 8. And that's going to, so you're going to original divided by new. Okay, original divided by new, and that's going to be how it got flipped and moved over. All right, every input of x got changed by 0.1, so that's going to scale the inputs by 0.1. That would be correct. That would be okay, right? That's okay, he's right. On the next page here, the function has an x in front of it, and you can tell us by graphing it. If you graph this or graph this, this goes through 0, 0. Because if you put a 0 there, everything cancels out and you get 0 out. If you put a 0 here, right? So the original goes through 0, 0. So does it go down? No, it goes up, right? So Claire is wrong, right? Because it goes up. It doesn't go down through negative 100. It goes up through 100. So it moved up, not down. And then if you put a negative in front, that always flips it over the y-axis. No, silly gooses. When you put a negative in front, it flips it over the, that's right, x-axis. Not the y. No. All right, now, we've kind of done this before. We want to change it from days to weeks. So each day is worth a day, but then we're going to change it into weeks. So what we need to do is we need to say that 1 week is equal to 7 days. So if you put in 1 week, you got to multiply by 7 to make it be into days. So 1 week would be 7 days, right? So you're going to multiply by 7 to make it, to change it the right way. So we're going to say G of W is equal to 30 times 2 to the 7W power. It's kind of tricky, but that's what we're doing. We're changing it that way. Now we're into the review questions. All right, review questions. So it says we have a hot air balloon here. It goes up, so it's just going to rise up. How many minutes will it take to get to 200 feet? So 16m is equal to 200. So if we solve that equation, we get how long it takes. So it goes up 16 for each minute. So 1 minute went up 16, 2 minutes up 32, 3 minutes up 48, etc. So we divide 200 divided by 16 is equal to 12 and a half. So 12.5 minutes. Let's put that graph on this page here. So at 12 and a half minutes, it's up at 200. So the hot air balloon rises. So at 12 and a half minutes, it's at 200 feet. And this is the F equation. Now what happens? This is review. So 5 minutes later, another balloon takes off. So we're going to write G of t in terms of the hx f of m. It's using m's. Wow, all these things are changing so fast. So we have G of m is equal to, we're shifting it 5 minutes later, so that means the graph's going to move 5 minutes to the left. So it'll be 16 times m minus 5. So it's just 5 minutes later. So let's have the same slope, right? But it's just 5 minutes later because it's going to be to the left 5 spaces. So we're going to make it be 5 minutes later. So we just 5 minutes later, start 5 minutes later, it's going to have the same exact slope. So 5 minutes later means at 17 and a half minutes, it would be at 200 feet. I don't think I got that lined up perfectly. It should be over here more. These should be parallel. Number 5. Odd function. Odd function has origin symmetry. So does this have origin symmetry? What do you think? I'm not thinking so much. The last question, number 6 here, is we're going to figure out what to do to this equation to make it match this data. All right. So in the calculator, I'm going to put 1.05. I'm going to raise it to the 5th power. Okay. Well, that's not this answer here, is it? So that would be equal to 1.2. So I need to take 1.2762 something, right? Multiply it by some number to get the 15.7. So you're changing this into this, but you need the scale factor to do that. So I'm going to divide back 15.7 divided by this last answer is 12.3. Okay, so I need a scale factor of 12.3 to do this. So 12.3 times 1.05 t is equal to P of t, the population. So let's check this out. Does this work? If I do 12.3, and then I'm going to do 1.05 to the power of 15. That's pretty close with rounding, isn't it? So that would be that. So you just have a couple of blanks to fill in, and then you're good.